October 3rd, 2025. The date astronomers had circled in red for months. The day when 7 spacecraft orbiting Mars would turn their cameras toward the most mysterious visitor our solar system has seen in years. 7 orbiters, 2 from NASA, 2 from the European Space Agency, 1 from China, 1 from the United Arab Emirates, all positioned perfectly to capture the highest resolution images ever taken of an interstellar object. The high-rise camera aboard NASA's Mars Reconnaissance Orbiter alone promised resolution down to 30 kilometers per pixel, 20 times sharper than anything Hubble had managed. This should have been the day we finally got answers about 3I Atlas. Instead, it became the day the silence started. 2 days before the flyby, October 1st, the United States government shut down. NASA's website went dark with a simple message. The agency is closed due to a lapse in federal government funding, and when the European Space Agency finally released images 4 days later, all we got was a fuzzy white dot moving across a field of stars. 1 image from 7 spacecraft. Where are the rest of the photos? What did those cameras really see when 3I Atlas passed within 30 million kilometers of Mars? And why, after months of anticipation, does it feel like someone just pulled the curtains closed, right as the show was about to begin? Before we dive into what might be one of the strangest cover-ups in astronomy, do me a quick favor. Hit that like button and subscribe if you haven't already. Then drop a comment telling me where you were listening from, what time it is there, and whether you think NASA's silence is bureaucracy or something more deliberate. And if you want to help grow our community, share this video on X, Facebook, Reddit, or your messenger. Thank you for always having our back. Chapter 1, The Perfect Setup. Let me take you back to July 1st, 2025. The Atlas telescope in Rio Hurtado, Chile, picks up something moving fast through the outer solar system. Within hours, astronomers pull pre-discovery images from archives, images taken by other Atlas telescopes around the world and by the Zwicky Transient Facility at Palomar Observatory. The object had been photographed as far back as June 14th, but nobody had noticed it yet. When they plot its trajectory, something immediately stands out. This thing isn't orbiting the Sun, it's passing through 3I Atlas, as it would come to be known, the 3rd interstellar object ever confirmed, after Oumuamua in 2017 and Borisov in 2019. But unlike those previous visitors, 3I Atlas arrived with something extra, a trajectory that seemed almost too perfect to be random. Think about the plane of our solar system, that flat disk where all the planets orbit, most objects coming from interstellar space approach from random angles. Oumuamua came in at 123 degrees relative to the ecliptic, Borisov at 44 degrees, 3I Atlas 5 degrees, 5 degrees from perfectly aligned with the plane, where all our planets live. Avi Loeb at Harvard ran the numbers. The probability of an interstellar object arriving within 5 degrees of the ecliptic plane just by chance sits around 0.2%, 1 in 500. Now add this. 3I Atlas would pass close to Mars. Within 30 million kilometers on October 3rd, it would swing near Venus. It would approach Jupiter in March 2026. The combined probability of an interstellar object arriving on a trajectory that brings it near 3 major planets in sequence, purely by random chance, 0.005%, 5 in 100,000. You start to understand why some researchers raised eyebrows. Natural comets don't typically come gift-wrapped with optimal viewing angles, but the trajectory was just the beginning. As summer progressed and more telescopes turned toward 3I Atlas, the data started accumulating. Hubble Space Telescope captured images in late July when the object sat 277 million miles from the Earth. What those images showed challenged expectations. Most comets, when you photograph them, show a bright nucleus with a tail streaming behind them. away from the sun. Solar radiation and solar wind pushed dust and gas backward, creating that classic comet tail we all recognize. 3I Atlas had something different. The Hubble image showed a glow, yes, but it extended forward, toward the sun, not away from it. The plume of scattered sunlight stretched out ahead of the object, like it was pushing through something rather than being pushed, and behind it, where you would expect a prominent tail, nothing. Just a faint suggestion of material that didn't show up clearly. Until late August, David Jewett at UCLA processed those Hubble images. He measured the forward glow extending several arcseconds. When you translate angular measurements at that distance into actual size, the bright region stretched across thousands of kilometers. But here's what made us astronomers pause. The extension was roughly 10 times longer than it was wide, creating an elongated teardrop shape pointing sunward. Natural outgassing. From a comet, nucleus tends to create more symmetric patterns, especially when solar radiation pressure should be actively pushing material backward. The James Webb Space Telescope observed 3I Atlas on August 6th, using its near-infrared spectrograph. Webb can break down the chemical composition of objects by analyzing the specific wavelengths of light they emit or absorb. What Webb found was unusual. The gas cloud surrounding 3I Atlas was dominated by carbon dioxide, 87% by mass. Carbon monoxide made up about 9%. Water, the primary component of most comets we've studied, comprised only 4%. Think about every comet humanity has observed from our own solar system. They're typically water-rich, icy bodies that formed in the cold NASA's spectrophotometer for the history of the universe. When they approach the sun and warm up, water ice sublimates, creating those brilliant tails we associate with comets. But 3I Atlas seemed to be built differently. 87% carbon dioxide is almost unheard of. Only one other comet in our record shows anything similar. Comet C, 2016 R2, discovered by Pan-STARRS, which also displayed an unusually high carbon dioxide to water ratio. The Spheric Space Observatory, NASA's spectrophotometer for the history of the universe. Epoch of ionization and ice explorer, observed 3I Atlas between August 7th and 15th. Spherex operates in the infrared, particularly at wavelengths around 1 micrometer, which helps estimate the size of objects by measuring how much sunlight they reflect. The data Spherex collected suggested something even more surprising. Based on the amount of infrared light bouncing off 3I Atlas, the nucleus could be as large as 46 kilometers in diameter, 46 kilometers for context. 2I Borisov, the previous interstellar comet, had a nucleus estimated around 1 kilometer. 3I Atlas, if the Spherex measurements hold up, could be 1,000,000 times more massive. 1,000,000 times, Havelock published his analysis of what this size discrepancy might mean. He calculated that at solid density, if 3I Atlas really is that large, we're talking about a minimum mass of 33 billion tons. That's his lower limit estimate. The object could be substantially larger. He pointed out something that makes the statistics even more troubling. If interstellar objects follow a normal size distribution, we should have detected hundreds or thousands of smaller objects before ever encountering something this massive. The Atlas telescope system has been scanning the sky for a decade. In all that time, just 3 interstellar visitors, and the third one is suddenly 1,000,000 times bigger than the second. The probability curve doesn't support that distribution, unless, of course, the size estimates are wrong, unless what Spherex detected wasn't the nucleus itself, but an enormous cloud of dust surrounding a much smaller core. That creates its own problems. If 3I Atlas has a dense dust coma large enough to reflect that much infrared light, where's the tail? Solar radiation pressure should push all that dust backward, creating a spectacular tail visible in every image. Instead, Hubble and other telescopes saw mostly forward, scatter, and minimal trailing material. Throughout August and September, ground-based observatories captured additional data. The Very Large Telescope in Chile performed spectroscopy on 3I Atlas on August 25th. They detected cyanide CN molecules being released from the object at a rate of about 20 grams per second, when 3I Atlas sat at 2.85 astronomical units from the Sun. But what caught attention was how rapidly that production rate increased. As the comet approached the Sun, the cyanide emissions scaled with heliocentric distance raised to the power of negative 9.4. That's an extraordinarily steep relationship. Most comets show production rates that scale with distance, raised to the power of negative 2 to negative 4. Negative 9.4 is almost unheard of. The VLT data revealed something else unusual. They detected nickel in the gas plume around 3I Atlas, but not iron. Nickel without iron. In nature, these two elements almost always appear together because they're both produced in supernova explosions and get incorporated into forming solar systems in relatively fixed ratios. Finding nickel without iron is like finding smoke without fire. It happens in very specific industrial processes where nickel alloys are manufactured. But in natural space objects, it's anomalous. Then, in early September, amateur astrophotographers Michael Yeager and Gerald Raymond captured images of 3I Atlas during a total lunar eclipse. Their photograph showed something unexpected. The comet, which had appeared reddish in all previous spectroscopic studies, now glowed green. Green comets aren't uncommon. The color typically comes from diatomic carbon molecules, C2, which fluoresce green when excited by solar ultraviolet light. But here's the problem. Earlier spectroscopic observations by Luis Salazar Manzano's team at the University of Michigan found that 3I Atlas showed extreme carbon chain depletion. The comet had significantly lower levels of C2 and C3 molecules than any other comet on record. If 3I Atlas lacks diatomic carbon, what's causing the green glow? One possibility. The steep increase in cyanide production detected by the VLT. Cyanide can produce greenish emissions under certain conditions. But again, the chemistry doesn't quite add up. The combination of high carbon dioxide, low water, depleted carbon chains, abundant cyanide, nickel without iron, and now a green glow that shouldn't exist. Based on the molecular inventory, it paints a picture of an object that doesn't quite fit any template we have for natural comets. By late September, 3I Atlas had moved close enough to the Sun that observing it from Earth became difficult. The geometry placed the comet near the Sun's position in our sky, drowning it in solar glare. From Earth-based telescopes, 3I Atlas effectively vanished into the brightness. This is where Mars became critical. Mars sits much farther from Earth than the Moon, but in early October 2025, Mars occupied a position in its orbit that gave spacecraft around the red planet a much better viewing angle of 3I Atlas. As Earth lost its line of sight, Mars gained one. 7 orbiters circled Mars, each equipped with cameras and spectrometers, designed primarily for studying the Martian surface, but capable of being repurposed for special observations. NASA's Mars Reconnaissance Orbiter carried the HiRISE camera, high-resolution imaging science experiment, arguably the most powerful camera ever sent to another planet. HiRISE can resolve features down to 35, come from its orbital altitude around Mars, pointed at 3I Atlas during closest approach. HiRISE's angular resolution translated to about 30 kilometers per pixel. That's resolution 20 times better than what Hubble achieved. When imaging the object in July, NASA's MAVEN spacecraft, Mars Atmosphere, and Volatile Evolution mission carried the imaging ultraviolet spectrograph, which could analyze the ultraviolet emissions from 3I Atlas and map the distribution of gases in its coma. The European Space Agency's Mars Express orbiter had the high-resolution stereo camera, along with Omega and SpyCam spectrometers for compositional analysis. ESA's ExoMars Trace Gas orbiter featured the Color and Stereo Surface Imaging System, KSSIS, plus the Nomad spectrometer and ISEM infrared instrument. China's Tianwen-1 orbiter contributed the moderate-resolution imaging camera. The UAE's Hope orbiter brought the Emirates Exploration Imager and 2 spectrometers, EMIRS and EMUS, 7 spacecraft, multiple cameras, multiple spectrometers, all positioned to capture data during 3I Atlas's closest approach to Mars on October 3rd. Astronomers worldwide anticipated this would provide the clearest look yet at the interstellar visitor. The pieces were in place. The timing was perfect. The instruments were ready. And then, 2 days before the event, the United States federal government shutdown. Chapter 2. The Silence Protocol. When a government shutdown occurs, certain agencies go dark while others maintain skeleton crews for essential operations. NASA typically furloughs around 80% of its workforce during these events. Public affairs offices close. Social media goes quiet. The main website displays that standard message about lapsed funding. But mission-critical operations continue. The Mars orbiters don't stop functioning. The instruments don't power down. Data still flows from spacecraft to ground stations, gets recorded, gets stored. What changes is the pipeline for public release. NASA's raw image archives for Mars missions normally update continuously. The Perseverance rover, for instance, uploads images from its various cameras to a public server where anyone can browse through them during normal operations. These raw images appear within hours of being taken, sometimes faster. The system is largely automated, but processing those raw images into calibrated, analyzed, publication-ready formats requires human expertise. It requires scientists to examine the data, correct for instrumental artifacts, stack multiple exposures if needed, and prepare explanatory materials for public consumption. On October 1st, 2025, that human expertise got furloughed. Over 15,000 NASA employees received notices. The timing meant that when 3I Atlas made its closest approach to Mars on October 3rd, the people who would normally process and release spacecraft imagery were at home, technically prohibited from performing official duties. The European Space Agency, not subject to United States funding politics, continued operations normally. ESA's Mars Express and ExoMars Trace Gas orbiter both observed 3I Atlas as planned. Between October 1st and 7th, these spacecraft turned their cameras toward the interstellar visitor. The ExoMars TGO used its CASIS camera to capture a series of 5-second exposures. Mars Express attempted observations with its high-resolution stereo camera, though the exposure time of half a second proved insufficient for detecting such a dim, distant target. On October 7th, 4 days after the Mars flyby, ESA released the CASIS images publicly. The scientific community and space enthusiasts, who had been waiting with anticipation, finally had something to examine. What they saw was a fuzzy white dot moving across a star field. Background stars appeared as streaks because CASIS tracked the moving comet during the exposure. 3I Atlas itself appeared as a slightly elongated blob, bright in the center, diffuse at the edges. The images confirmed 3I Atlas existed, confirmed it had passed by Mars as predicted, but revealed little about its structural composition. Nick Thomas, principal investigator for the CASIS instrument, explained the challenge. CASIS was designed to photograph the bright surface of Mars from just a few hundred to a few thousand kilometers away. Pointing it at a dim object 30 million kilometers distant pushed the instrument well beyond its intended operating parameters. The comet appeared roughly 10,000 to 100,000 times fainter than typical targets. The fact that CASIS detected anything at all demonstrated impressive versatility, but the resolution was limited. Loeb analyzed the CASIS images in detail. He noted that the width of the bright glow around 3I Atlas in those pictures measured about twice the diameter of background stars in the same frame. Given the angular resolution of Cassis, this translated to roughly 680 kilometers of visible coma. That's an order of magnitude smaller than what Hubble had observed. But Hubble had much longer exposure times and much larger aperture. Cassis could only detect the brightest central region, missing the fainter outer envelope that extended much farther. The interesting detail, Loeb pointed out, was that the extension of scatter light around 3I Atlas appeared qualitatively, similar to what Hubble had captured back in July, just compressed into a smaller apparent size. Due to instrumental limitations, the data suggested no major increase in outgassing had occurred over the intervening months. If 3I Atlas were a typical comet approaching the Sun, you would expect activity to ramp up dramatically as solar heating intensified. The relatively stable appearance implied either the object wasn't responding to solar heating the way normal comets do, or its response was more subtle than expected. Meanwhile, speculation about NASA's images intensified. 7 spacecraft had been in position. The Mars Reconnaissance Orbiter's high-res camera should have captured extraordinarily detailed views. MAVEN's ultraviolet spectrograph should have mapped the gas distribution. Yet nothing appeared in public archives. The automated raw image feeds from the Perseverance rover continued updating, showing the usual surface geology of Jezero Crater, but no official processed images of 3I Atlas materialized. On October 4th, just one day after the flyby, something appeared in the Perseverance raw image archive that caught attention. The right navigation camera, one of the rover's nav cams used primarily for surface navigation, had captured an image at 21:33 local solar time on Mars. The image showed an elongated streak of light against the dark sky. The timestamp coincided with when 3I Atlas would have been visible from Mars. Amateur astronomers immediately began downloading and analyzing the image. Simeon Schmaus, an astrophotographer who regularly processes publicly available space mission data, stacked multiple navcam frames together to boost faint details. He identified what appeared to be a smudge of light in the constellation, Corona Borealis, close to where orbital calculations predicted 3I Atlas should appear. Stephen Burns created a 9-minute time-lapse by stitching together sequential navcam images, showing a bright object moving across the Martian sky. But the morphology of that streak raised questions. The object in the navcam composite appeared roughly 4 times longer than it was wide, creating a cylindrical or cigar-shaped appearance. Social media corrupted with comparisons. Someone noted it resembled the Doomsday Machine from the 1960s Star Trek episode, a massive cylinder that consumed planets. Others pointed out the similarity to Oumuamua, which had also displayed an elongated shape, though Oumuamua's length-to-width ratio was closer to 10:1 based on its light curve variations. Was 3I Atlas actually cylindrical, or was something else creating that appearance? Abe Loeb addressed the question in a detailed analysis. He calculated that the navcam image was likely a composite stack of hundreds of individual frames, taken over approximately 10 minutes. During that time, 3I Atlas would have been moving across the Martian sky at significant apparent velocity. Mars orbits the Sun at 24 kilometers per second. 3I Atlas was traveling at 67 kilometers per second, relative to the Sun in a retrograde direction opposite to Mars. The relative velocity between the comet and Mars translated to a path length of roughly 50,000 kilometers over a 10-minute integration period. If amateur astronomers stack all those frames together without accounting for the object's motion, it could create a streak. The length of that streak would depend on how long the stacking process integrated, not on the actual physical dimensions of 3I Atlas. Individual snapshots, with navcam's maximum exposure time of 3.28 seconds, would show 3I Atlas as a roughly circular spot. Stacking them creates the illusion of elongation. Think of it like photographing a car, driving down a highway at night with a long exposure. The car itself might be compact, but in your photo, it appears as a long streak of light. The streak doesn't represent the car's actual shape, just its motion during the exposure. The same principle applies here. The cylindrical appearance in the amateur-processed images likely results from motion blur, not from 3-eye atlas being physically elongated. Still, NASA hadn't confirmed whether the NavCam images even showed 3-eye atlas. The agency remained silent. The featured image of the week on NASA's Mars Reconnaissance Orbiter page for the week of September 28th through October 4th included a NavCam image from Perseverance, but no accompanying explanation identified what the bright object was. Given the government shutdown and the furloughed public affairs staff, perhaps that silence was understandable, but the lack of clarity left room for speculation to flourish. Then came reports, unverified but circulating through space enthusiast communities, that NASA had provided preliminary briefings to select mainstream media outlets on October 4th, just 24 hours after the flyby. These briefings allegedly characterized 3-eye atlas as an ordinary comet without addressing any of the anomalous features that had puzzled astronomers. No supporting technical reports accompanied these briefings. No images were released, just verbal assurances that everything was normal. Dr. Michael Salla, who runs the Exopolitics website and has spent decades researching government secrecy around space-related topics, pointed out a pattern. He traced the history of how NASA handles potentially controversial imagery back to 2 whistleblowers who came forward in 2001, Donna Hare, who worked as a technical illustrator for NASA contractor Philco Ford, and Carl Wolf, a sergeant in the United States Air Force with a top-secret crypto clearance. Both testify at the Disclosure Project press conference and organized by doctors. Stephen Greer. Hare described her work at the Lunar Receiving Laboratory at Johnson Space Center, where she had security clearance to enter certain areas. She testified that she witnessed NASA photo lab technicians airbrushing anomalies out of lunar photographs before their public release. She spoke with multiple agency insiders who Wolf affirmed this was standard procedure. Wolf testified about his experience at Langley Air Force Base, working on photographic equipment used to process imagery from the lunar orbiter missions. He claimed to have seen photographic evidence of artificial structures on the far side of the moon, evidence that was classified and removed from public versions of the imagery. Whether you believe those testimonies or not, they established the precedent for what Salla calls scrubbing, the systematic removal of potentially controversial elements from space imagery before public release. A technique evolved over decades. In the early days of Mars exploration, orbiters provided live feeds that anyone monitoring the right radio frequencies could receive. When anomalies appeared in those live feeds, words spread quickly through amateur radio communities. NASA's solution was to eliminate live feeds in the International Space Station, occasionally broadcast live video of live Earth from its external cameras. Multiple times over the years, viewers have reported seeing objects in those feeds that defy easy explanation. Strange lights, structured shapes, moving in unusual patterns. Whenever such objects appear, the feed cuts to a colored screen or switches to a different camera angle. NASA typically attributes these interruptions to signal loss or routine camera switching, but the timing often coincides suspiciously with whatever anomaly viewers were watching. Mars missions followed a similar evolution. Early missions released imagery quickly, often within hours. But as public interest grew and as image analysis tools became more sophisticated, NASA implemented more layers of review. Images now go through calibration processes, artifact removal, quality checks, and explanatory review before public release. This serves legitimate scientific purposes. Raw spacecraft data can be noisy, can contain instrumental glitches, and can be misinterpreted without proper context. But it also creates a buffer period during which problematic imagery can be identified and handled differently. Michael Salla proposed that the current situation with 3I Atlas fits this pattern. 7 spacecraft photographed the object. At least some of those spacecraft, particularly the Mars Reconnaissance Orbiter, with its powerful high-res camera, must have captured clear, detailed images. The absence of those images in the public record, even as automated raw feeds continue from other instruments, suggests someone made a decision about what to release and what to withhold. Consider the sequence of events. October 1st, government shutdown begins. October 3rd, 3I. Atlas passes close to Mars. October 7th, European Space Agency releases fuzzy images from Cassius. October 8th, 9, 10, 11, 12, NASA remains silent. No processed images. No technical reports. No scientific papers analyzing the Mars flyby data. Radio silence. Avi Loeb commented on the situation during an interview with NBC News. He addressed the question directly. Whether the government shutdown represented some kind of conspiracy to hide information about 3I Atlas. His response was characteristically dry. The delay, he said, is not the signature of extraterrestrial intelligence. It's more a signature of terrestrial stupidity. He acknowledged the frustration, but attributed the silence to bureaucratic dysfunction, rather than deliberate concealment. Perhaps that's accurate. Perhaps the silence really does come down to furloughed employees and stalled workflows, but the timing remains remarkable. After months of anticipation, after perfect positioning of multiple spacecraft, after the astronomical community circled October 3rd as the date when we would finally get definitive answers about this strange visitor, the curtain came down at the exact moment the show was supposed to start, and that pattern, whether intentional or coincidental, plays into a longer history of opacity around space missions. The public wants transparency. Scientists want data, but institutional inertia, classification protocols, and image processing pipelines create bottlenecks, where information goes in but doesn't always come out, at least not quickly, and sometimes not at all. Chapter 3, Behind the Sun. October 29th, 2025 approaches. This date carries significance because it marks perihelion, the point where 3I Atlas reaches its closest distance to the Sun, at 1.36 astronomical units, roughly 203 million kilometers, placing the comet just inside the orbit of Mars. For observers on Earth, this creates a geometric problem. 3I Atlas will be positioned almost directly behind the Sun from our perspective, hidden in solar glare, completely unobservable from ground-based telescopes. This blackout period extends from late October through most of November. Earth-based astronomers lose visual contact with the interstellar visitor, precisely when it should be at its most active. Solar heating intensifies dramatically as objects approach perihelion. Comets typically display peak outgassing during this phase. Their ice is sublimating rapidly under intense radiation. If 3I Atlas truly is a natural comet, perihelion should trigger spectacular activity. Bright jets of gas and dust, potentially even fragmentation if thermal stress exceeds structural integrity. But we won't be able to watch it happen from Earth. The Sun blocks our view completely. This isn't unusual. Comets pass behind the Sun regularly, and astronomers simply wait for them to emerge on the other side. What makes this situation different is the constellation of questions already surrounding 3I Atlas, the anomalous chemistry, the unusual trajectory, the missing Mars flyby images. All of it compounds into a scenario where the object disappears from observation at the most critical moment. Avi Loeb pointed out the implications in one of his October blog posts. If 3I Atlas is a natural comet, perihelion might cause it to break apart. Thermal stress and tidal forces from the Sun's gravity can tear fragile icy bodies into pieces. Comet Shoemaker-Levy 9 famously fragmented when it passed too close to Jupiter in 1992, torn apart by tidal forces. before the pieces crashed into the gas giant. Other comets have disintegrated when approaching the Sun, unable to withstand the heating. Jets of sublimating gas can also spin up a comet's rotation. If outgassing isn't distributed evenly across the surface, it creates torque, acting like tiny thrusters that accelerate the nucleus. Fast rotation introduces centrifugal forces. Comet 332P/Ikea-Murakami broke apart in 2016, likely due to rapid spin induced by asymmetric outgassing. If 3I Atlas fragments at perihelion, Earth-based observers will see multiple pieces emerge in early December, instead of one coherent object. But Loeb also outlined an alternative scenario. If 3I Atlas is technological, if the object is a spacecraft rather than a natural comet, perihelion provides a unique opportunity. Hidden behind the Sun from Earth perspective, the object could maneuver without being observed. It could use solar gravity to perform a gravitational assist, altering its trajectory in ways that would be impossible for a passive rock. It could release smaller craft, mini probes that separate from the main body and take up different orbits. The retrograde trajectory becomes significant here. 3I Atlas moves opposite, the direction planets orbit around the Sun. From the object's reference frame, planets are approaching it rather than receding. This geometry makes intercept calculations simpler. A probe released from 3I Atlas with velocity, partly opposed to the main body's motion, could slow down relative to the Sun, dropping into a bound orbit rather than continuing on a hyperbolic escape trajectory. Those probes could then wait, positioned along orbital paths where they would eventually encounter Earth, Venus, or Mars as those planets continue their circuits around the Sun. Think of it like dropping breadcrumbs along a hiking trail. You don't need to aim each crumb at a specific target. You just need to place them along the path you know hikers will follow. The retrograde orbit of 3I Atlas means its released probes would naturally intersect planetary orbits, simply by reducing their velocity relative to the Sun. The timing would depend on when and where the releases occurred. But the geometric setup favors eventual encounters. This scenario assumes intent, assumes technology, assumes a level of capability that strains credulity for most scientists. But Loeb has never shied from exploring low-probability possibilities. When they remain consistent with available data, he rates 3I Atlas a 6 out of 10 on what he calls the Loeb scale, where 0 represents a definitely natural object and 10 represents a definitely artificial. 6 suggests genuine uncertainty, enough anomalies to warrant serious consideration, but not enough evidence to reach definitive conclusions. Presenting 11 different theoretical frameworks for understanding 3I Atlas. These range from completely natural explanations, large comet with unusual chemistry, to various technological scenarios. Extraterrestrial reconnaissance probe, abandoned generation ship, deliberately sent contact craft, hostile weapon system. Sala doesn't endorse any single interpretation but argues that institutional science prematurely closes off possibilities without thorough investigation. One of Sala's more intriguing suggestions involves what he calls the white hat hypothesis. According to this framework, 3I Atlas represents a cooperative effort between positive, extraterrestrial civilizations and reform-minded elements within Earth's military and intelligence communities. The object supposedly generates frequency codes, energetic patterns that influence consciousness and accelerate spiritual awakening. The timing of its arrival, Sala argues, coincides with increasing disclosure efforts, with more whistleblowers coming forward, with growing public awareness of classified programs. This kind of speculation obviously ventures far beyond mainstream scientific discourse. It mixes ufology, consciousness studies, geopolitics, and fringe physics into a narrative that most academics would dismiss outright. But Sala has cultivated an audience over decades by documenting patterns in government secrecy, tracking whistleblower testimonies, and proposing frameworks that attempt to make sense of seemingly disconnected, anomalous phenomena. Whether those frameworks accurately describe reality or represent elaborate pattern-matching exercises imposed on random data remains hotly debated. What's undeniable is that gaps in official information create space for speculation to thrive. When NASA doesn't release expected imagery, when agencies go silent during critical observation windows, when data that should be public remains locked away, people naturally construct explanations to fill those voids. The perihelion passage presents another element of this dynamic. From late October through most of November, no Earth-based telescope can observe 3I Atlas. The object exists in a blind spot, hidden behind 200 million kilometers of solar plasma. Space-based observatories positioned at different angles might maintain line of sight, but those missions have their own targeting constraints and data release schedules. Yes, as Jupiter Icy Moon's explorer, the JUICE mission finds itself in a favorable position. JUICE launched in April 2023, currently en route to Jupiter via a complex trajectory involving multiple gravitational assists. In November 2025, JUICE will be positioned such that 3I Atlas becomes visible from its vantage point, and the comet will have just passed perihelion, potentially displaying maximum activity. Between November 2nd and 25th, JUICE will observe 3I Atlas using several instruments. The Janus camera system can capture optical images. The major spectrometer maps composition in visible and infrared wavelengths. The UVS ultraviolet spectrograph analyzes gas emissions. The PET particle detector measures the interaction between solar wind and the comet's outgassing. This multi-instrument approach should provide comprehensive data about 3I Atlas's behavior during its most active phase. But there's a catch. JUICE currently operates in a communications-constrained environment. The spacecraft is close to the Sun from Earth's perspective, using its high-gain antenna as a heat shield. Communications rely on the medium-gain antenna, which transmits data at much slower rates. Additionally, JUICE sits on the far side of the Sun relative to Earth, meaning signals must traverse a longer path through the solar system. The combination of these factors means data from the November observations won't reach Earth for months. ESA estimates that data from the 3I Atlas observations won't be available for analysis until February 2026, 3 months after the observations. 3 months during which the scientific community and interested public will have no information about what happened at perihelion. 3I Atlas will emerge from behind the Sun in early December, visible again from Earth-based telescopes. But the crucial perihelion period remains a black box until the Jupiter arrives. Then there's the Juno spacecraft. NASA's mission currently orbiting Jupiter. Juno arrived at the gas giant in July 2016 and has been studying Jupiter's atmosphere, magnetic field, and gravitational structure ever since. The mission has been extended multiple times, with operations continuing through at least September 2025. In theory, Juno could observe 3I Atlas as the comet passes through Jupiter's vicinity in March 2026, except NASA deactivated Juno's cameras. The Juno Cam, a visible light imager included primarily for public outreach, was switched off in September 2025, just weeks before 3I Atlas would enter Juno's observable region. The official explanation cited power budget constraints and the need to prioritize scientific instruments. Juno Cam was always considered a bonus instrument, not part of the core mission objectives. Shutting it down to conserve power for other systems makes operational sense, but the timing strikes some observers as suspicious. Juno could have provided close-range imagery of 3I Atlas during its Jupiter flyby, offering perspectives unavailable from any other spacecraft. Instead, the cameras go dark right before the opportunity arises. Coincidence or coordination? Depending on your prior assumptions about institutional transparency, you interpret this differently. What's objectively true is that 3I Atlas enters a series of observation gaps precisely when it should be most interesting. Earth-based telescopes lose sight in late October. Juno's cameras are offline. JUICE captures data but won't transmit it until February. The Mars orbiters, that could have provided detailed imagery in early October, remain silent. Their data unreleased or possibly restricted. The result is a months-long blackout where our most mysterious interstellar visitor in years operates beyond scrutiny. If 3i Atlas behaves exactly like 2i Borisov did during its 2019 perihelion passage, displaying typical cometary activity, fragmenting naturally or remaining intact and continuing on its hyperbolic trajectory without deviation, then the speculation will seem overblown in hindsight. But if 3i Atlas does something unexpected, if it maneuvers, if it releases objects, if its trajectory shifts in ways that can't be explained by outgassing or gravitational interactions, we won't know until after the fact. And even then, without continuous observation data, distinguishing between what happened naturally and what might have been deliberate becomes nearly impossible. This uncertainty extends to ground-based observers as well. Amateur astronomers equipped with telescopes in the 8-inch diameter range or larger should be able to spot 3i Atlas when it emerges from solar glare in early December. The comet's predicted brightness around magnitude 10 places it within reach of serious amateur equipment. Networks of amateur observers will undoubtedly turn their instruments skyward, eager to capture images after the long blackout period. But what they see will represent the aftermath, not the event itself. If 3i Atlas fragmented at perihelion, they'll observe multiple pieces. If it remained intact, they'll track one object. If it maneuvered, they might notice the trajectory deviates from predictions. But reconstructing exactly what happened during the unobserved period requires inference, orbital mechanics calculations, and comparative analysis with pre-perihelion data. The direct observational record will have a gap that no amount of post-analysis can completely fill. This brings us back to the question of institutional and national responsibility. When government agencies like NASA possess capabilities that private citizens and even most academic institutions lack, those agencies become gatekeepers of information. If they release data promptly and comprehensively, the scientific community and public can evaluate evidence collectively. If they delay releases, restrict access, or provide selective information, they create information asymmetries that fuel suspicion. Chapter 4. The Mass Problem. Let's return to something that deserves more attention than it initially received. The size estimates for 3i Atlas vary so wildly depending on which instrument and which measurement technique you use that reconciling them becomes a puzzle in itself. This isn't just academic bean counting. The mass of 3i Atlas directly impacts every other inference we make about its nature. Start with the early observations from ground-based telescopes. When astronomers first detected 3i Atlas in July, they calculated its brightness and used standard assumptions about reflectivity to estimate size. If you assume an object has an albedo, that's reflectivity of 0.05, which is typical for cometary nuclei. You can work backward from how much light it reflects to determine how large it must be. Those initial estimates suggested a diameter around 10 to 20 km. Then, Hubble observed 3i Atlas on July 21st. The images showed a diffuse glow extending several arcseconds, but determining the actual nucleus size from that glow proved difficult. Cometary comas, the clouds of gas and dust surrounding the nucleus, can be much larger than the solid core. Hubble's resolution limited how precisely astronomers could measure the boundary between nucleus and coma. By August 20th, after additional observations, Hubble data suggested the nucleus diameter fell somewhere between 440 meters and 5.6 km. That's an upper limit of 5.6 km, meaning the actual size could be anywhere in that range. 5.6 km at the high end. But remember the Sphere X measurements. The infrared observations in mid-August implied a diameter of 46 km, not 5.646, an object almost 9 times larger in diameter, which translates to roughly 700 times more massive if you assume similar density. Have you, Loeb, explored what this discrepancy might mean? One possibility: the Spirex measurements captured reflected sunlight from a massive dust cloud, rather than from the nucleus itself. If 3I Atlas is surrounded by an enormous coma of dust particles, each individually microscopic but collectively vast, they could reflect enough infrared light to make the whole system appear as large as 46 km. But this explanation creates that problem we touched on earlier. Where's the tail? Solar radiation pressure pushes dust away from the sun. A dust cloud large enough to mimic a 46-kilometer nucleus would produce a spectacular tail visible in every optical image. Yet most observations show minimal tail development. The alternative explanation, the one that makes the statistics uncomfortable, is that the nucleus really is that large. If the solid core of 3I Atlas measures 46 km across, and if we assume something close to solid ice density, around 1 gram per cubic centimeter, the math yields a mass seating 33 billion tons. Loeb calculated this as a lower limit. If the density is higher, if the object contains significant rocky material mixed with ice, the mass could be substantially greater. Now think about discovery statistics. The Atlas telescope network has surveyed the sky for over a decade, specifically looking for near-Earth objects and other transient phenomena. In all that time, we've detected 3 interstellar objects. 1, I Oumuamua, measured around 100 meters in diameter. It is roughly football field sized. 2, I Borisov, measured around 1 kilometer. Then 3I Atlas at potentially 46 kilometers. That's a jump of 46 times in size, representing roughly a million-fold increase in mass. Size distributions in nature typically follow power laws. Smaller objects are exponentially more common than larger ones. This holds true for asteroids, for comets, for planets, for stars. If you survey a population and find the size distribution, you should detect many small objects for every large one. The ratio varies depending on the specific population, but the pattern holds remarkably consistent across different astronomical contexts. If interstellar objects follow a similar distribution, we should have detected hundreds or thousands of 1-kilometer objects like Borisov before ever encountering a 46-kilometer object like 3I Atlas might be. The probability of seeing the sequence we've actually observed: 1 small object, 1 medium object, then immediately a giant, doesn't match any reasonable size distribution model, unless the observations are wrong, unless 3I Atlas isn't actually 46 kilometers, unless the infrared measurements misinterpreted something about the object's properties or geometry. This brings us back to the question of what exactly is reflecting that infrared light. One proposal suggests 3I Atlas might be a rubble pile, a loosely bound collection of smaller fragments rather than a single coherent nucleus. Rubble pile structures are common among asteroids and some comets. They form when gravitational attraction holds fragments together without fully consolidating into solid rock. The gaps between fragments create internal voids. When a rubble pile comet approaches the sun, solar heating can vaporize ices deep within the structure, creating internal pressure that forces gas to escape through surface vents. If 3I Atlas is a rubble pile with a highly porous structure, its effective size could be large while its mass remains modest. Imagine a snowball compared to an equal volume of loosely packed snow. The snowball is dense and compact. The loose snow occupies the same space but contains much more void and much less actual material. A 46-kilometer rubble pile could have a mass similar to a 10-kilometer solid nucleus if the bulk density is low enough. But rubble pile structures also affect how objects respond to thermal stress. The internal voids provide insulation. Heat doesn't penetrate as efficiently. Outgassing can be more violent because pressure builds up internally before finding escape routes. The observable signatures of a rubble pile versus a solid nucleus differ in subtle but measurable ways. Spectroscopic studies of gas production rates, thermal emission patterns, rotation state changes, all of these provide clues about internal structure. So far, the observations of 3I Atlas don't clearly favor either interpretation. The rapid increase in cyanide production as the comet approached the Sun suggests some kind of temperature-dependent chemical process, but whether that indicates solid or rubble pile structure remains ambiguous. The unusual chemical composition, carbon dioxide dominated with low water content, could result from formation in a particularly cold region of some distant protoplanetary disk, or it could indicate substantial processing, either through long-term exposure to cosmic rays, during interstellar travel, or through some other mechanism. There's another angle to consider. What if 3I Atlas contains a solid core, surrounded by a much larger but tenuous cloud of material? Not a traditional coma of gas and dust, but something more structured. Some comets exhibit what are called dust trails, streams of larger particle that spread out along the comet's orbital path. These trails can extend for millions of kilometers, but remain too diffuse to create visible tails in the usual sense. If 3I Atlas is shedding material in a particular pattern, perhaps creating an envelope of particles that travels with the nucleus, that envelope could reflect infrared light in ways that make the system appear larger than the core actually is. The challenge with all these explanations is that they're constructed to fit the data after the fact. We observe something anomalous, then generate hypotheses that might explain it. But without detailed spatial resolution, without being able to actually see the structure we're theorizing about, distinguishing between competing models becomes difficult. The Mars flyby in early October should have provided that spatial resolution. He says 30 kilometer per pixel capability would have resolved a 46 kilometer object as a distinct disk rather than a point source. We would have seen structure, maybe even surface features, if the resolution was good enough. But we don't have those images. Or rather, they presumably exist somewhere in NASA's data archives, but haven't been made public. The European images from Cassini lack sufficient resolution to answer the size question definitively. So we're left with this uncertainty, a factor of 9 difference between the lower and upper estimates, a difference that completely changes the statistical implications and the physical interpretation of what 3I Atlas represents. He emphasized that the size determination from the upcoming observations, particularly if NASA eventually releases the high-res data, will be crucial for evaluating whether 3I Atlas fits natural population models. If the nucleus is small, under 10 kias, the statistical argument weakens. We can explain 3I Atlas as an unusually bright comet with unusual chemistry, but still fundamentally natural. If the nucleus is large, approaching that 46 kilometer estimate, the statistical argument strengthens. The object becomes harder to explain as a random draw from natural interstellar comet populations. This connects back to the broader question of how common interstellar objects are. Before Oumuamua, we had theoretical predictions, but no observational constraints. The detection of 3 interstellar objects in 8 years gives us a rough estimate of their space density. Based on that detection rate and accounting for survey limitations, astronomers calculate there might be 1 interstellar object within Earth's orbit at any given time. As we move farther from the Sun, the density increases. At the distance of Neptune, there could be dozens. At the distance of the Oort cloud, thousands. These estimates depend on assumptions about size distributions. If most interstellar objects are small, the space density could be higher. If they're predominantly large, density must be lower to match the observed detection rate. The statistics form a constraint web. Change one assumption, and you must adjust others to maintain consistency with what we actually see. 3I Atlas stresses the constraint web specifically because of its size ambiguity. A 46-kilometer interstellar object shouldn't be the third one we detect. Statistically, we should find smaller objects first, lots of them, before getting lucky enough to spot a giant. The fact that we might have found a giant third suggests either we've been extraordinarily lucky, which is always possible, or the size distributions don't work the way we assume, or the object isn't what it appears to be. That last possibility is what keeps bringing discussions back to technological hypotheses. If 3I Atlas is artificial, if it's a constructed object rather than a natural comet, the size statistics don't constrain it. An advanced civilization capable of interstellar travel would build whatever size spacecraft serves their purposes. They're not subject to the natural distribution of icy rubble in the galaxy. A 46-kilometer spacecraft is extravagant by human standards, but we have no reference frame for what alien engineering might consider standard. Of course, proposing that 3I Atlas is artificial because it violates statistical expectation for natural objects is circular reasoning of the most obvious kind. We don't have enough data to establish solid statistical expectations in the first place. 3 detections over 8 years provides a sample size of 3, drawing firm conclusions about population distributions. From 3 data points is premature at best, but that's precisely the frustration. We need more data. We need better observations. We need the kind of detailed imaging and spectroscopy that multiple spacecraft were positioned to provide in early October, and we're stuck waiting for institutions that move slowly, that have layers of review, that operate under constraints both budgetary and political. Meanwhile, 3I Atlas continues its journey. It crossed Mars' orbit. It's approaching perihelion. Soon it will be behind the Sun, unobservable from Earth, doing whatever comets or spacecraft or whatever it is do when nobody's watching. The mass question remains unresolved. The size ambiguity persists, and the statistical arguments for or against natural origins remain suspended in uncertainty, waiting for data that may or may not eventually arrive. Chapter 5. The Origin Question. Where did 3I Atlas come from? Not in the immediate sense of its trajectory through our solar system. That's well established, but in the deeper sense of which star system originally birthed this object billions of years ago. Tracing interstellar objects back to their sources presents immense challenges. These objects have been traveling through this galaxy for eons, experiencing gravitational perturbations from passing stars, interactions with molecular clouds, and the cumulative effects of galactic rotation. Small uncertainties in current velocity measurements amplify exponentially as you extrapolate backward, through millions or billions of years. A Team LED by Matthew Hopkins at the University of Oxford tackled this problem using the Otatahi-Oxford model, a sophisticated simulation that combines data from the Gaia spacecraft's stellar census with models of protoplanetary disk chemistry and galactic dynamics. They input 3I Atlas's observed velocity and position, then ran the trajectory backward through time, tracking which stars the comet might have passed near during its journey. The key parameter is velocity. When 3I Atlas arrived in our solar system, it was moving away from the galactic center at 51 kilometers per second. It was also moving upward through the galactic plane at 18.5 kilometers per second. That vertical component, the W velocity, in galactic coordinates is unusually high. Most nearby stars and most objects in the solar neighborhood have lower vertical velocities, typically under 10 kilometers per second. The stars and objects in the galactic disk orbit mostly in the plane, with some wobbling motion up and down. But 3I Atlas's vertical velocity exceeds that typical wobble. This suggests 3I Atlas belongs to what astronomers call the thick disk population, rather than the thin disk. The Milky Way's disk actually has 2 components. The thin disk contains younger, metal-rich stars with composition similar to the Sun, orbiting in a relatively flat plane. The thick disk contains older metal-poor stars, formed when the galaxy was younger and less chemically enriched, orbiting in a more vertically extended distribution. Objects from the thick disk typically have higher vertical velocities because their orbital planes are tilted relative to the main galactic plane. If 3I Atlas came from the thick disk, it's likely old. Hopkins and colleagues estimated its age at between 7.6 and 14 billion years old. With 68% confidence, the Sun, for reference, is 4.6 billion years old. 3I Atlas could predate our entire solar system by billions of years. It might have formed when the universe was less than half its current age, making it a relic from an earlier epoch of galactic history. An independent analysis by Astro Taylor, Darrell Seligman reached similar conclusions, estimating 3I Atlas at 3 to 11 billion years old. The range is wide because converting galactic kinematics into age estimates requires assumptions about how the thick disk formed and evolved. But both studies agree 3I Atlas represents an ancient object, something that has been wandering the galaxy for an extraordinarily long time. The chemical composition supports this interpretation. Thick disk stars have lower metallicity than thin disk stars. Metallicity in astronomy refers to the abundance of elements heavier than hydrogen and helium. The early universe contained essentially only hydrogen and helium. Stars fuse those light elements into heavier ones: carbon, oxygen, nitrogen, silicon, iron. When stars die, especially in supernova explosions, they scatter those heavier elements into the interstellar medium. Subsequent generations of stars and planets form from gas clouds enriched with these metals. Thick disk stars formed earlier, before as much metal enrichment had occurred. Planets and comets forming in those systems would have compositions reflecting the lower metal abundances of their birth environments. If 3I Atlas formed in a low metallicity protoplanetary disk, its composition would differ from solar system comets. The high carbon dioxide to water ratio might indicate formation beyond the carbon dioxide frost line in a disk, with particular temperature and chemical gradients. All of this points towards 3I Atlas, originating from an old star system in the thick disk. But which specific star a team LED by Yi Yang Guo attempted to trace 3I Atlas backward through the galaxy to identify possible parent stars. They used Gaia data covering over 13 million stars, running simulations to determine which stars 3I Atlas might have passed within close range during the past 10 million years. Close range in this context means within about 6.5 light years, 2 parsecs. At that distance, stellar gravity could potentially perturb an object's trajectory enough to capture it into a bound orbit, or eject it into interstellar space. The simulations identified 93 nominal encounters, stars that 3I Atlas passed relatively near during its reconstructed path. Of those, 62 were significant at the 2 sigma confidence level, meaning the orbital uncertainties didn't completely rule them out. But here's the problem. None of those encounters produced meaningful perturbations. The strongest potential perturber, a star cataloged as Gaia Dr. 36863-591, 38952-9611264, passed within 0.3 parsecs of 3I Atlas with a relative velocity of 35 kilometers per second. That interaction should have changed 3I Atlas's velocity by about 5/10,000ths of a kilometer per second. That's negligible. To put it in perspective, 3I Atlas currently moves at 60 kilometers per second. A velocity change of half a meter per second is utterly insignificant. The conclusion: no stellar flyby within the past 10 million years, and within 500 parsecs of the Sun can account for 3I Atlas's current trajectory. The comet wasn't recently ejected from any nearby star system. It's been traveling through interstellar space for much longer than 10 million years, potentially hundreds of millions or even billions of years. This creates a fascinating but sobering picture. 3I Atlas is a wanderer in the truest sense. It formed around some unknown star billions of years ago. Gravitational interactions, probably with a giant planet or a close stellar encounter, kicked it out of its birth system. Since then, it's been drifting through the galaxy, occasionally passing through star systems like ours, but mostly traveling through the vast empty spaces between stars. During that journey, cosmic rays have bombarded its surface. Interstellar dust grains have sandblasted it. Ultraviolet. Light from distant stars has processed its surface chemistry. All of these effects alter the object's properties over time, changing its composition in ways that might mask its original chemical signature. This is why comparing 3I Atlas to solar system comets provides only limited insight. Solar system comets are pristine, preserved in cold storage in the Oort cloud, or Kuiper belt since the solar system formed 4.6 billion years ago. 3I Atlas has been exposed to the interstellar environment for potentially 3 times that long. The thick disk. Origin also raises questions about formation conditions. Stars in the thick disk often have planetary systems. The Kepler mission and other exoplanet surveys have detected planets around metal-poor stars, but the characteristics of those planetary systems differ from systems around metal-rich stars. Lower metallicity means less solid material available during planet formation. Rocky planets might be smaller or rarer. Gas giants might form differently. The architecture of planetary systems, the spacing and masses of planets, correlates with the metallicity of the host star. If 3I Atlas formed in a low metallicity system, it might represent the kind of cometary material typical of thick disk planetary systems, rather than thin disk systems like ours. Its unusual composition could be normal for its population, even if it seems strange, compared to what we're familiar with in our solar system. But all of this remains speculative. We can't definitively identify the parent star. We can't reconstruct the detailed history of 3I Atlas's journey. We can characterize its current velocity and infer population membership, thick disk versus thin disk, but the specific story of where it came from and what happened along the way remains lost in the statistical noise of galactic dynamics. Some researchers have explored whether 3I Atlas, Oumuamua, and Borisov might be related, perhaps ejected from the same star system at different times, or even from the same parent comet that fragmented. The velocities don't support this hypothesis. Oumuamua and Borisov arrived from completely different directions, with different speed vectors. 3I Atlas's velocity is also distinct. The 3 objects don't trace back to any common origin within recent galactic history. They're truly independent visitors, each carrying its own unique story. This independence actually strengthens the case that interstellar objects are common. If we've detected 3 completely unrelated visitors in 8 years, it suggests the galaxy is filled with these wanderers. The space between stars isn't empty. It's populated with countless rocks and ice balls, debris from planet systems across the Milky Way, all drifting on their own trajectories, occasionally crossing paths with star systems like ours. Most of these objects are too small to detect. We only spot the ones that happen to pass close enough, and happen to be large enough or active, enough to reflect sufficient light for our telescopes. The detection threshold biases our sample toward larger, brighter objects. The actual population includes vastly more smaller bodies that we simply can't see. This leads to predictions about future discoveries. The Vera C. Rubin Observatory, previously called the Large Synoptic Survey Telescope, is scheduled to begin full operations in late 2025. Rubin will survey the entire visible sky every few nights, cataloging everything that changes or moves. The sensitivity and coverage will enable detection of many more interstellar objects, potentially dozens per year once the survey reaches full capacity. Those future detections will finally provide the statistical sample needed to characterize interstellar object populations properly. We'll measure the size distribution, the velocity distribution, the composition distribution. We'll identify rare outliers and common types. We'll develop a taxonomy for interstellar visitors, the same way we have taxonomies for asteroids and comets in our own solar system. 3I Atlas in this context represents a pioneer. It's one of the first arriving before we have the systematic survey capabilities to put it in proper context. That makes it simultaneously fascinating and frustrating. Fascinating because every detail matters when your sample size is 3. Frustrating because interpreting those details without comparative population data requires educated guessing. But the age of 3I Atlas adds a philosophical dimension to these considerations. This object is 10 billion years old. It formed when the universe looked different. The Milky Way was younger, more chaotic, with active star formation throughout the disk. Galaxies were colliding and merging more frequently. The cosmic environment differed in fundamental ways. An object that old has witnessed the evolution of the galaxy, has been traveling through space longer than Earth has existed. Our entire solar system, our planet, all of life's history on Earth, everything we know and care about. All of it occurred while 3I Atlas was already ancient, already wandering between the stars. There's something humbling about that perspective, about encountering a messenger from the deep past, from a time and place we can never visit, but can dimly reconstruct through astronomy. If 3I Atlas could speak, if we could somehow extract the full history encoded in its composition and structure, what would it tell us? What stars has it passed? What events has it witnessed? Has it entered other planetary systems before ours? Have other civilizations observed it? Perhaps even studied it the way we're attempting to now? These questions venture into speculation, but they're not scientifically empty. They motivate the effort to study interstellar objects in detail. Every measurement, every spectrum, every image adds a piece to the reconstruction of that history. We're archaeologists, in a sense, examining artifacts from distant times and places, trying to read the stories written in chemistry and physics. Chapter 6. The Awaiting Observers. December 2nd, 2025. That's when ESA's JUICE spacecraft begins its observation. Campaign of 3I Atlas. By this time, the comet will have passed perihelion, emerged from behind the sun, and entered its most active expected phase, solar heating. During the close approach, should trigger maximum outgassing. If 3I Atlas is a natural comet, December will display its full glory. Bright coma, prominent tail, possibly even fragmentation debris. If thermal stress exceeded structural limits, JUICE, the Jupiter Icy Moons Explorer, wasn't designed with interstellar comet observations in mind. The mission targets Jupiter's large moons, Europa, Ganymede, and Callisto, searching for evidence of subsurface oceans and assessing habitability. The scientific payload includes cameras, spectrometers, radar, magnetometers, particle detectors, all optimized for studying icy moon geology and potential habitable environments. But in November 2025, JUICE finds itself at the right place and right time to observe 3I Atlas. The spacecraft will employ multiple instruments. JANUS, the Jovian Aurora Nocturnum Undique Scrutator, translates loosely as All-Around Jupiter Observer, is an optical camera system with 13 filters covering wavelengths from 360 to 1080 nanometers. It can capture color, images, and perform basic compositional analysis based on spectral reflectance. MAGIS, the Moons and Jupiter Imaging Spectrometer, covers visible to infrared wavelengths, mapping composition in much finer spectral detail than JANUS. The UVS, ultraviolet spectrograph, analyzes emissions in the extreme and far ultraviolet, particularly useful for detecting specific molecules like water, carbon monoxide, and hydrogen. Then there's the PEEP instrument, Particle Environment Package. PEEP actually comprises 6 different sensors measuring electrons, ions, and neutral atoms across a wide energy range. When a comet outgasses, those released molecules and particles interact with the solar wind. Some get ionized by solar ultraviolet light. Some undergo charge exchange reactions. The result is a complex particle environment surrounding the comet that PP can characterize, revealing details about the composition and rate of outgassing that optical observations alone can't access. The advantage JUICE holds over Earth-based observations at this time comes down to geometry. When 3I Atlas emerges from behind the Sun in early December, it will be visible from Earth again, but the viewing angle will be constrained. We'll see it from one direction only, JUICE, positioned elsewhere in the solar system. We'll observe from a different angle. A combination of perspectives, Earth-based and JUICE-based, enables stereoscopic reconstruction of the coma structure. Imagine trying to understand the 3-dimensional shape of a cloud. By looking at it from directly below, you see a 2-dimensional projection, a blob in the sky. But you can't determine its depth or true extent. Add a second viewpoint from the side, and suddenly the 3-dimensional structure becomes clear. That's what multi-angle observations provide. They turn flat projections into spatial maps. Additionally, JUICE will observe 3I Atlas just after perihelion, catching it in a potentially more active state than Earth-based telescopes were in summer and early autumn. If perihelion triggered enhanced outgassing, if jets became more prominent, if the color or composition of the coma changed due to thermal processing, JUICE will document those changes while they're still fresh. But all of this comes with the caveat already mentioned. The data won't arrive until February 2026, 3 months after the observations, 3 months during which the world will watch 3I Atlas through ground-based telescopes comparing its post-perihelion behavior to pre-perihelion behavior, noting any changes, any anomalies, any deviations from predicted trajectories. The JUICE data will eventually provide additional context, but not in real time. Ground-based observations will resume once 3I Atlas separates sufficiently from the Sun's position in the sky. But you'll capture data that adds to the collective understanding, and when dozens or hundreds of amateur observers around the world all point their equipment at the same target, the aggregate data set becomes substantial. 3I Atlas will likely receive this kind of attention: the controversy, the speculation, the institutional silence. All of it creates public interest. When people care about an object, when they want answers, they direct resources toward it. Amateur networks will coordinate observation campaigns. They'll share timing windows. They'll process each other's data. They'll compare notes about what they're seeing. If 3I Atlas does something unexpected, amateur observers will catch it. If the brightness suddenly increases in an outburst, someone will notice within hours. If the trajectory deviates from predictions, orbital analysis enthusiasts will flag the discrepancy. If multiple objects appear where one used to be, indicating fragmentation, images will document it. The global network provides redundancy. No single point of failure exists. The object can't disappear into institutional secrecy when thousands of independent eyes are watching. But observers will only see what's visible after perihelion, the critical moment, the passage behind the Sun, the time when thermal stress peaks, and when any hypothetical maneuvering or probe deployment would most logically occur. That moment remains unobserved from Earth. JUICE data will help reconstruct what happened, but 3 months delayed. The immediate post-perihelion observations will show results, not causes. This creates an interpretive challenge. Suppose 3I Atlas emerges from perihelion on a slightly different trajectory than predicted. Not wildly different, just a few tenths of a % deviation. That level of change could result from outgassing. Jets of gas escaping from the nucleus create tiny thrust forces over weeks and months. Those forces accumulate into measurable velocity changes. It's called the rocket effect, and it's well documented among comets. Knowing that rocket effect exists, how do you distinguish between natural outgassing that happens to push the comet slightly off course and deliberate maneuvering that mimics natural outgassing? You can't, not conclusively. You can model expected outgassing based on solar heating and estimated nuclear size. You can measure actual outgassing by observing the coma brightness and spectroscopic emission lines. If the observed outgassing accounts for the trajectory change, you invoke natural causes. If the trajectory change exceeds what the observed outgassing should produce, you have an anomaly. But the measurements come with uncertainties. The models have assumptions. Distinguishing signal from noise requires careful analysis. Or suppose 3I Atlas fragments. Comets fragment relatively often. Thermal stress causes cracks. Rotation creates centrifugal forces. Internal pressure from vaporizing ices finds weak points and tears the structure apart. If 3I Atlas emerges as multiple pieces, is that natural fragmentation or deliberate separation of a mothership from daughter probes? Again, you need additional evidence to distinguish. Natural fragments follow ballistic trajectories determined by the breakup geometry. They separate slowly, typically at velocities of meters per second or less. Deliberate probes could have higher separation velocities. They could maneuver independently after separation. They could display non-gravitational accelerations that natural fragments wouldn't exhibit. But detecting those signatures requires precise astrometry over extended periods. You need to track each fragment's position with high accuracy, night after night, week after week, building up enough data to fit orbital models and look for deviations. This brings us back to the question of institutional capabilities versus citizen science capabilities. A professional observatory can provide the astrometric precision needed for these analyses. The tracking cameras used for near-Earth asteroid surveys, like the Atlas network itself, achieve positional accuracies of fractions of an arc-second over weeks of observations. That precision enables orbital determinations, good enough to predict positions months or years in advance, and to detect subtle non-gravitational forces. Amateur equipment generally can't match that precision. An 8-inch telescope might achieve astrometric accuracy of 1 to 2 arc-seconds under good conditions, but that's an order of magnitude worse than professional instruments. For bright objects moving slowly across the sky, amateur astrometry suffices. For faint objects moving quickly, requiring high precision to detect small deviations, professional resources become necessary. This is where the institutional silence matters. If NASA and ESA release data promptly, if professional observatory coordinate observation campaigns, if the global astronomical community brings its full resources to bear, we maximize the scientific return from this rare opportunity. If data gets bottlenecked, if observations are delayed, if coordination fails, we learn less than we could. The Galileo Project, LED by Avi Loeb, represents an attempt to bridge this gap. The project operates 3 observatories, one in Massachusetts, one in Pennsylvania, one in Nevada, equipped with instruments specifically designed to detect and characterize anomalous aerial phenomena. The observatories use multiple camera systems, covering visible and infrared wavelengths, along with environmental sensors, to correlate detections with atmospheric conditions, while the Galileo Project's primary focus is UAP, unidentified anomalous phenomena in Earth's atmosphere. The observatories can also track objects in space. Loeb state that the Massachusetts Observatory will monitor the sky during and after 3I Atlas's perihelion passage, looking for any correlated increase in UAP activity. The hypothesis being tested is whether an interstellar object's arrival might trigger secondary phenomena, either through natural physical processes we don't yet understand, or through hypothetical probe deployments. This crosses from conventional astronomy into more speculative territory. The scientific mainstream, would argue there's no reason to expect correlation between interstellar comet passages and atmospheric anomalies. But Loeb's approach is to collect data and look empirically, rather than assume the answer in advance. If there's no correlation, the data will show that. If there is correlation, it demands explanation. The broader point is that 3I Atlas has catalyzed multiple observation strategies. Professional, amateur, and purpose-built projects like Galileo. The object has captured attention in a way that transcends typical comet observation. Part of that stems from its interstellar origin. Part comes from the anomalous properties. Part results from the controversy and speculation. All of it combines to ensure that when 3I Atlas emerges from behind the sun, many eyes will be watching. Chapter 7. The Scientific Battleground. Jason Wright maintains a blog called Astro Wright, where he documents his work in astrophysics and occasionally critiques the work of others. In July 2025, he published a detailed analysis of Avi Loeb's claims about 3I Atlas. The title of the post, simply Avi and 3I Atlas, signals the direct nature of what follows. Wright doesn't mince words. He calls Loeb's alien spacecraft hypothesis nonsense and lays out a systematic rebuttal of each claimed anomaly. Wright is a professor of astronomy and astrophysics at Penn State University, director of the Penn State Extraterrestrial Intelligence Center, and a member of multiple scientific advisory boards. His credentials in the search for technosignatures, evidence of technological civilizations, match or exceed Loeb's. When Wright criticizes Loeb's work, it's not coming from a skeptic dismissive of all exotic possibilities. It's coming from a colleague in the same field who disagrees with the methodology and conclusions. The core of Wright's critique focuses on how Loeb handles evidence. Wright traces through Loeb's evolving statements about 3I Atlas chronologically. On July 2nd, Loeb's first blog post expressed excitement about the discovery, but mentioned nothing about alien spacecraft. On July 3rd, he appeared in a Daily Mail interview where the possibility of extraterrestrial technology got mentioned. By July 4th, Loeb was arguing the object must either be much smaller than initial estimates suggested, or statistically improbable. On July 7th, he was discussing intercept scenarios. By mid-July, he had fully committed to the hypothesis that 3I Atlas might be technological. Wright argues this progression reveals motivated reasoning. Rather than following the data to a conclusion, Loeb selected a conclusion early, and then highlighted evidence supporting it, while dismissing or minimizing evidence contradicting it. For instance, multiple observatories detected cometary activity around 3E Atlas, the presence of gas and dust creating a visible coma. Loeb acknowledged this initially, but then shifted to arguing the observations were inconclusive, that the fuzz seen around the object could result from instrumental effects or motion blur, rather than actual outgassing. The Very Large Telescope released images, clearly showing a symmetric coma around 3E Atlas, exactly what you expect from a comet. Loeb dismissed these images as inconclusive, given the object's motion and inevitable smearing. But Wright points out that the VLT team specific, they accounted for motion in their image processing. The images were not smeared artifacts. They showed genuine cometary activity. Wright also addresses the size argument. Loeb made much of the 10 to 20 kilometer size, estimate based on early brightness measurements, arguing this was too large to be consistent with interstellar comet populations. But as Wright notes, those were very preliminary estimates based on assumptions about albedo that might not hold. Subsequent observations suggested smaller sizes. Loeb then pivoted to the sphere X infrared measurements, suggesting 46 Quire. Using that as evidence, the object was anomalous. But Wright questions whether the infrared data really indicates nuclear size or just an extended dust cloud. Throughout his critique, Wright emphasizes that every supposedly anomalous feature of 3I Atlas has plausible natural explanations. The lack of a prominent tail could result from the viewing geometry or from the object being observed before significant outgassing began. The unusual chemical composition, carbon dioxide rich and water poor, is rare but not unprecedented. The trajectory alignment with the ecliptic plane is unlikely, but not impossibly so. Statistics measure probabilities, not impossibilities. Unlikely things happen. That's literally what unlikely means. It doesn't mean forbidden. Wright's frustration becomes evident when he discusses how Loeb's behavior affects the broader field of technosignature research. Wright and others working on the search for extraterrestrial intelligence need to maintain scientific credibility. They need funding agencies to take their proposals seriously. They need journals to publish their papers. They need colleagues to collaborate. When high-profile researchers make bold claims based on thin evidence, it affects the reputation of the entire field. Critics can point to the overreach and argue that technosignature research is inherently unserious, always reaching for the most exotic explanation, without proper scientific rigor. This creates tension within the SETI community. On one hand, the field needs visibility. Public interest drives funding. Media coverage attracts students. Provocative claims about possible alien artifacts generate attention in ways that dry technical papers don't. On the other hand, the field needs respectability. It needs to be seen as legitimate science, not as fringe speculation. Balancing those competing needs create ongoing debates about methodology, about standards of evidence, about how to communicate with the public. Loeb's response to critics has been consistent. He frames himself as a Galileo figure, a maverick challenging the orthodoxy. He argues that mainstream science is too conservative, too quick to dismiss unconventional ideas, too invested in protecting existing paradigms. He points out that throughout history, scientists who proposed radical new ideas faced resistance before eventually being vindicated. The subtext is that his critics are the modern equivalent of those who rejected Galileo, defending outdated models against uncomfortable truths. This narrative has rhetorical power. Everyone likes an underdog story. The image of a lone scientist bravely pursuing truth against institutional opposition resonates, but Wright and others argue it's misleading. Loeb isn't being persecuted. His papers get published. He holds a prestigious position at Harvard. He leads well-funded research projects. He appears regularly in media. If anything, he receives more attention than most scientists. The pushback he faces comes not from an orthodoxy trying to suppress him, but from colleagues pointing out methodological problems with his work. The scientific process includes criticism. When you propose a hypothesis, others examine it, test it, look for flaws. That's how science progresses. The fact that colleagues criticize Loeb's claims about Oumuamua doesn't mean they're closed-minded. It means they're doing their job, evaluating evidence and offering alternative interpretations. Some criticism is harsh, some is dismissive, but much of it is substantive, pointing to specific issues with data analysis or logical reasoning. Chris Lintott, professor of astrophysics at Oxford, called Loeb's Oumuamua alien probe hypothesis absolute nonsense. He emphasized that all available evidence points to Oumuamua being a comet with typical cometary properties, once you account for observational limitations and processing uncertainties. Other astronomers echoed this assessment, some publicly, some privately. The consensus view within the planetary science community is that 3I Atlas is natural, but consensus doesn't equal certainty. Science operates on provisional conclusions, subject to revision when new evidence emerges. It's entirely possible the majority view is wrong. History includes examples where scientific consensus later proved mistaken. Continental drift was dismissed for decades before plate tectonics gained acceptance. Prions, infectious proteins without nucleic acids, were considered impossible before Stanley Prusiner demonstrated their existence. The existence of extrasolar planets was doubted until the first confirmations in the 1990s. So the question becomes, What would constitute sufficient evidence to overturn the consensus that 3-eye atlas is natural? What observations or measurements would convince the skeptical majority that technological explanations deserve serious consideration? Loeb has proposed several criteria. If 3-eye atlas maneuvers in ways inconsistent with natural outgassing, that would be significant. If it releases objects that then display independent maneuvering, that would be nearly definitive. If it emits radio signals or other electromagnetic emissions, inconsistent with natural outgassing, that would be significant. With thermal radiation, that would be compelling. If detailed imaging reveals geometric structures, regular patterns, or other hallmarks of design, that would demand explanation. None of these signatures have been detected. 3-eye atlas hasn't deviated from predicted trajectories. Beyond what natural outgassing might cause, it hasn't emitted anomalous signals. No images show artificial structures. The object behaves like a comet in almost every measurable way. The only unusual features are the chemical composition, which is rare but naturally explicable, and the trajectory statistics, which are unlikely but not impossible. Given this situation, most astronomers argue that Occam's razor favors the natural interpretation. When you have two competing hypotheses that both explain the observations, prefer the simpler one. A comet with unusual but natural properties is simpler than an alien spacecraft designed to mimic a comet. The technological hypothesis requires assuming advanced civilizations exist, have interstellar travel capability, chose to visit our solar system, constructed their spacecraft to look like comets, and timed their visit to when we happen to have the technology to detect interstellar objects. That's a lot of assumptions stacked on top of each other. The natural hypothesis requires only that interstellar comets exist, which we've confirmed through 3 detections, and that some of those comets have unusual properties, which we'd expect given the diversity of planetary system formation conditions across the galaxy. That's far fewer assumptions, making it the preferred explanation, absent compelling evidence to the contrary. But Loeb would counter that this reasoning presumes we know the probability distribution for these various assumptions. How confident are we that alien civilizations are rare? How sure are we that interstellar travel is difficult? Do we really understand the range of motivations an alien civilization might have? The Copernican principle, the idea that we're not special or unique, suggests other civilizations probably exist somewhere. The Fermi paradox, the apparent absence of evidence for those civilizations, despite the high probability they exist, demands explanation. One resolution to the paradox might be that alien civilizations communicate or travel in ways we haven't recognized yet. Interstellar objects could be one such mode. This philosophical debate about priors, about what assumptions we bring to the evidence evaluation, underlies much of the controversy. Different scientists with different priors reach different conclusions from the same data. Those with very low priors for alien technology need overwhelming evidence to update their beliefs. Those with higher priors, like Loeb, update more readily on ambiguous evidence. There's no purely objective way to resolve this. Bayesian reasoning, the mathematical framework for updating beliefs based on evidence, requires specifying prior probabilities. Where do those priors come from? Partly from previous experience and data, but ultimately from judgment calls about how to weigh different possibilities. Scientists disagree about those judgment calls, leading to disagreements about interpretation, even when they agree about the raw observations. What's frustrating for all parties involved is the lack of definitive data. If the Mars flyby images had been released immediately, if they showed clear, detailed structure, much of the debate would be settled. If ground-based observations during perihelion were possible, if we could watch 3-eye atlas continuously through its most active phase, we'd have better constraints. Instead, we have partial data, delayed releases, observation gaps, and plenty of room for competing interpretations to persist. The scientific battleground over 3-eye atlas illustrates how astronomy works when dealing with rare, poorly observed phenomena. It's not clean. It's not decisive. It's a messy process of competing hypotheses, incomplete evidence, professional disagreements, and public speculation. Eventually, either 3I Atlas will do something unambiguous that forces consensus, or it will leave the solar system with its nature still debated. Another mystery added: the long list of unresolved questions about our universe. Chapter 8. The Social Media Storm. While scientists debated methodology and evidence standards in journals and blogs, a parallel conversation exploded across social media platforms. 3I Atlas became a trending topic on X, formerly Twitter, with thousands of posts analyzing images, sharing speculation, and spreading misinformation. Reddit communities devoted threads to tracking every development. YouTube creators published videos with titles promising shocking revelations. TikTok users created short clips explaining the comet or warning about potential dangers. The pattern follows: a familiar trajectory for astronomical phenomena that capture public imagination. Initial excitement spread through early adopter communities, astronomers, space enthusiasts, and science communicators. Then, mainstream attention kicks in as news outlets cover the story. From there, the narrative fragments into countless variations, as different voices add their interpretations, corrections, embellishments, and fabrications. Some social media discussion remained grounded in actual observations and scientific analysis. Amateur astronomers shared their telescope images, compared notes on visibility windows, and discussed processing techniques. Science communicators tried to provide accurate context, explaining what 3I Atlas is, where it came from, and why it's interesting. These posts often included disclaimers about uncertainty, acknowledgments of what we don't know, references to expert opinions, but other content veered into speculation unconstrained by evidence. Some posts claimed 3I Atlas was definitely an alien mothership, citing Avi Loeb's papers, while admitting his caveats. Others warned it posed an imminent threat to Earth, despite its trajectory staying far beyond Mars's orbit. Conspiracy theories proliferated. Some suggested governments were hiding the truth about 3I Atlas. Others connected it to unrelated events, political developments, economic predictions, religious prophecies. A particularly viral post falsely attributed statements to physicist Michio Kaku, claiming he said 3I Atlas was accelerating toward Earth with possible hostile intent. The post included a manipulated screenshot from a television interview. Kaku appeared on camera with text overlaid, suggesting he had made these dramatic claims. The image spread rapidly, accumulating hundreds of thousands of views before fact-checkers identified it as fabricated. The actual interview screenshot came from February 2025, months before 3I Atlas was even discovered. Someone had taken an unrelated Kaku appearance, added misleading text, and presented it as current news. This kind of manipulation happens frequently with scientific topics. Public figures get misquoted or have their statements taken out of context to support narratives they never endorsed. Al Jazeera's fact-checking operation, Sanad, investigated the Kaku claims and published a detailed debunking. They traced the image to its source, confirmed the date of the original interview, and found no record of Kaku making statements about 3I Atlas at all. But by the time fact-checks appeared, the false claims had already spread through networks of users who wanted to believe the dramatic narrative. This illustrates a fundamental challenge. In modern information environments, truth and fiction spread at different rates through different pathways. Accurate but mundane information. 3I Atlas is an interstellar comet, following a predictable trajectory that poses no threat to Earth, generates modest engagement. Sensational but false information. Scientists confirm alien spacecraft approaching Earth with hostile intent. Generates massive engagement because it triggers emotional responses: fear, excitement, curiosity. Platform algorithms optimize for engagement. Posts that generate clicks, shares, comments, and time on platform get amplified. Posts that users scroll past without interaction get buried. This creates selection pressure favoring content that provokes strong reactions regardless of accuracy. Content creators, whether they're motivated by genuine belief, desire for attention, or financial incentives from ad revenue, learn to craft messages that maximize engagement. The result is an information ecosystem where facts compete with fiction on unequal terms. Scientists carefully hedging their statements, with appropriate uncertainty qualifiers, get drowned out by confident voices making definitive claims, nuanced analysis requiring attention, and thought loses to simple narratives requiring only emotional reaction. The careful process of science, hypothesis, evidence, revision, and consensus building looks boring and slow compared to the rapid-fire provocations of social media discourse. 3i Atlas became a canvas onto which people projected their existing beliefs. Those already convinced that governments hide evidence of extraterrestrial contact saw the NASA silence as confirmation. Those skeptical of institutional authority interpreted the missing images as intentional concealment. Those interested in apocalyptic scenarios transformed the comet into a threat, despite its trajectory keeping it millions of kilometers from Earth. One persistent narrative claimed military forces were preparing to deflect or destroy 3i Atlas. Posts referenced alleged mobilizations, secret meetings at the Pentagon, and coordination between international defense agencies. These claims lacked any factual basis. No such mobilizations occurred. No credible sources reported military interest in 3i Atlas beyond standard space situational awareness that tracks all significant solar system objects. But the narrative persisted because it fit a particular worldview. If 3i Atlas is a threat, then, of course, military forces would respond. If governments hide information, then, of course, they wouldn't announce their plans. The absence of evidence becomes evidence of concealment. Every denial reinforces the conspiracy theory, because naturally conspirators would deny the conspiracy. This logical structure makes such theories unfalsifiable, immune to correction through normal means. Other social media users took a different approach, treating 3i Atlas as entertainment rather than genuine mystery. Memes proliferated. One popular format showed the doomsday machine from Star Trek with captions, joking about humanity's response to interstellar visitors. Another format used the disaster girl meme template with 3i Atlas, photoshopped into the background. These humorous takes acknowledge the speculation while maintaining ironic distance from it. This entertainment framing serves a social function. It allows people to engage with the topic without committing to specific beliefs. You can share a joke about 3i Atlas being an alien spacecraft without actually believing that claim. The humor creates common ground, a way to participate in the cultural moment around the discovery, without getting drawn into contentious debates about what's real. But humor and misinformation exist on a continuum. What starts as obvious satire can get taken, literally, by audiences who don't recognize the joke. Screenshots of satirical posts get shared without context. Parody accounts get mistaken for legitimate sources. The boundaries blur between entertainment, speculation, misinformation, and deliberate deception. Content moderation teams at social media platforms face difficult decisions. How do you handle posts making false claims about scientific topics? If someone says 3i Atlas is an alien spacecraft approaching Earth, is that dangerous misinformation requiring removal? Or is it protected speculation and opinion? Different platforms apply different standards. Some take a hands-off approach, allowing most content unless it directly incites violence or harassment. Others try to attach warning labels or fact-check notices to dubious claims. Neither approach fully solves the problem. Heavy moderation risks, censoring legitimate debate, and fueling complaints about platform bias. Light moderation allows misinformation to spread unchecked. The scale of content, millions of posts per day across multiple platforms, makes consistent enforcement nearly impossible. Automated systems flag potential violations, but they make mistakes, removing innocent content while missing actual problems. For researchers studying 3i Atlas, this social media storm creates additional complications. When you're trying to communicate scientific findings to the public, you're competing with a flood of other voices, some helpful, many not. Journalists contact scientists for quotes, but those quotes might get used in articles, alongside unvetted speculation from random social media users, presented as equally credible. The signal-to-noise ratio becomes overwhelming. Some scientists engage directly on social media, trying to provide accurate information and correct misconceptions. Avi Loeb maintains an active presence on X, posting links to his blog articles and responding to questions. Other astronomers use Twitter threads to explain orbital mechanics or interpret new observations. These efforts reach audiences who might not read scientific papers or visit astronomy websites, bringing expert knowledge into spaces where misinformation otherwise dominates. But social media engagement requires time and energy. Scientists have day jobs teaching, research, writing papers, attending conferences, spending hours on Twitter, responding to questions and debunking false claims. Diverse effort from those core activities. Not every scientist has the inclination or skill for public communication. Some prefer to let their works speak through formal channels, rather than engaging in online debates. This creates an asymmetry. Those most motivated to spread sensational claims often have more time to dedicate to social media than working scientists. A researcher might post an accurate explanation once, then move on to other tasks. Meanwhile, multiple accounts continue pushing false narratives, responding to comment, and sharing memes, keeping their version of events circulating. Volume overwhelms quality. Then there's the question of what happens when the scientific consensus itself is uncertain. With 3i Atlas, experts genuinely disagree about some interpretations. Loeb thinks the anomalies warrant considering technological hypotheses. Wright thinks natural explanations suffice. How do you communicate that disagreement to a public audience without creating the impression that scientists don't know anything, that everything is equally uncertain? The scientific method embraces uncertainty as a feature, not a bug. Theories remain provisional, subject to revision with new evidence. Confidence levels vary depending on how much data supports a conclusion. This nuance to epistemology doesn't translate easily into social media discourse, where users expect definitive answers when a scientist says we're not sure yet. Audiences sometimes hear scientists are clueless, rather than understanding that uncertainty is an honest assessment of current knowledge. NASA's attempt to address public concerns about 3i Atlas illustrates these communication challenges. As viral posts spread, false claims about the comet's trajectory and alleged threat to Earth, the agency tried to provide reassurance. Their official statements emphasize that 3i Atlas poses no danger, that its closest approach to Earth was millions of kilometers away, that the trajectory is well understood and predictable. But for audiences already suspicious of NASA, these reassurances had limited effect. If you believe agencies lie about extraterrestrial matters, then official denials carry no weight. In fact, they might strengthen suspicion. This dynamic traps institutions in a no-win situation. Remaining silent feeds conspiracy theories about concealment. Issuing denials feeds conspiracy theories about cover-ups. No response strategy fully addresses concerns from audiences operating with different epistemological frameworks. The broader pattern extends beyond 3i Atlas to science communication generally. Whenever a topic captures public attention, climate change, vaccines, artificial intelligence, space exploration, the same dynamics emerge. Experts try to provide accurate information constrained by appropriate uncertainty. Activists and advocates push specific interpretations aligned with their values. Opportunists exploit attention for personal gain. Conspiracy theorists weave the topic into existing narratives. Comedians and meme creators use it for entertainment. All of these voices compete for attention in a shared information space where distinction between expertise and opinion get flattened. Maybe the solution requires rethinking how scientific institutions interact with public audiences. Current approaches, press releases, occasional interviews, official statements were designed for an era when media gatekeepers controlled information flow. Journalists vetted sources, provided context, separated signal from noise. That system had its own problems and biases, but it created some filtration. Social media eliminated those gatekeepers. Anyone can publish directly to global audiences. This democratization brings benefits, diverse voices, rapid information sharing, grassroots organization, but it also brings challenges: misinformation, manipulation, and algorithmic amplification of extreme content. Adapting scientific communication to this environment remains an ongoing experiment with uncertain outcomes. Chapter 9. The December Emergence. Early December 2025 will mark a pivotal moment. 3i Atlas, after weeks hidden behind the sun, will emerge into observable positions for ground-based telescopes. The geometry will place it low in the pre-dawn sky initially, visible for only a couple of hours before sunrise. Venus will be nearby, bright and obvious, providing a reference point for locating the much fainter comet. The predicted magnitude, around magnitude 10, places 3i Atlas at the edge of what binoculars can detect under dark sky conditions. An experienced observer with good equipment might pick it up as a fuzzy patch distinct from background stars. But for clear confirmation, you need a telescope. 8 inches of aperture provides comfortable margin. Larger instruments will show more detail, potentially revealing the coma structure, maybe even a faint tail if one is developed. What observers see during those first nights will answer immediate questions. Is 3i Atlas intact? Does it appear back as a single object or multiple fragments? Has the brightness changed dramatically from pre-perihelion observations? Is there visible tail development? Does the trajectory match predictions or show deviations? These observations will come from dozens of locations simultaneously. Amateur astronomy clubs coordinate observation campaigns through online forums and email lists. Someone in Australia gets the first look as 3i Atlas rises. Above their eastern horizon, they post initial reports, brightness estimates, descriptions of what they're seeing. Hours later, observers in the Middle East pick up the watch. Then Europe, then the Americas. The relay continues, building a continuous observational record spanning days and weeks. Professional observatories will join the effort. Survey telescopes that normally track asteroids will point at 3i Atlas, measuring precise positions for astrometric analysis. Spectroscopic facilities will analyze the chemical composition of the coma, checking whether perihelion altered the outgassing mix. Photometric monitors will track brightness variations that might indicate rotation or outburst activity. The data will flow into databases maintained by the Minor Planet Center, the International Astronomical Union's clearinghouse for observations of comets, asteroids, and other small solar system bodies. Astronomers worldwide will access this data, fitting orbital models, comparing observations across different instruments and locations, and looking for patterns or anomalies. If 3i Atlas fragmented during perihelion, the first observations will reveal multiple objects where one used to be. Each fragment will have its own, slightly different trajectory based on the separation velocity and direction during breakup. Tracking those fragments over subsequent nights will allow reconstruction of when and how the breakup occurred. Natural fragmentation typically produces pieces that drift apart slowly, meters per second relative velocity. The fragments stay relatively close together for weeks before gradually separating into distinct orbits. But suppose the observations show something different. Suppose multiple objects appear, but their separation velocities are higher than natural fragmentation would produce. Or suppose the objects display non-gravitational accelerations, velocity changes, that can't be explained by outgassing from their surfaces. That would demand explanation. You would need to consider whether something other than simple fragmentation occurred. This scenario remains speculative, as no current evidence suggests 3I Atlas will fragment at all. Many comets survive perihelion passages intact, especially if their perihelion distance stays outside about half an astronomical unit. 3I Atlas at 1.36 AU sits comfortably beyond that danger zone. Thermal stress will be significant, but probably not catastrophic. The object should emerge intact, unless its internal structure is unusually weak or unless something other than natural comet behavior is occurring. The trajectory question becomes critical during December observations. Orbital predictions based on pre-perihelion data assume only gravitational forces act on 3Y Atlas. The Sun's gravity dominates. Jupiter's gravity contributes smaller perturbations, and the other planets make tiny contributions. Add those forces together, integrate the equations of motion forward in time, and you get predicted positions for any future date. But comets experience non-gravitational forces from outgassing. When jets of gas escape the nucleus, they create thrust, changing the comet's velocity slightly. These changes accumulate over time. For a comet with vigorous outgassing, non-gravitational forces can alter the trajectory, enough to produce noticeable position errors after weeks or months, if you ignore them in your models. Astronomers account for this by adding non-gravitational acceleration terms to their orbital models. These terms have parameters that get fitted to the observations, treating the outgassing thrust as unknowns to be solved for, along with the orbital elements. If the fitted parameters are consistent with observed outgassing, if the amount of thrust matches what you would expect from the measured gas production rates, then you conclude natural processes explain the trajectory. But if the trajectory deviations exceed what observed outgassing should produce, you have a problem. Either your outgassing measurements are incomplete, missing some component of the activity, or some other force is acting on the object. This is where careful observation becomes crucial. You need comprehensive spectroscopy. To measure all the gas species being emitted, you need photometry to track coma brightness as a proxy for activity level. You need precise astrometry to measure positions accurately. Correlating all these measurements allows disentangling natural outgassing effects from potential other influences. December observations will provide the first test of whether 3I Atlas's post-perihelion trajectory matches predictions. The data will accumulate night by night after a week of observations. Preliminary orbital fits will narrow the uncertainties. After 2 weeks, the constraints tighten further. By the end of December, astronomers will have a solid handle on where 3I Atlas is going and whether its path deviates from expectations. If deviations appear, the scientific community will debate their significance. Small deviations, within the range explainable by outgassing, will generate papers analyzing the non-gravitational forces, but won't trigger major controversy. Large deviations, changes that seem inconsistent with natural comet behavior, will trigger intense scrutiny. Researchers will check for instrumental errors, systematic biases in the observations, and alternative explanations. Only after exhausting conventional possibilities would attention turn to unconventional hypotheses. Meanwhile, the JUICE spacecraft will be conducting its own observations between November 2nd and 25th. Those observations overlap with the period when 3I Atlas is still behind the Sun from Earth's perspective. This will see the comet during and immediately after perihelion, capturing data about its most active phase. But that data won't reach Earth until February 2026. This creates a strange informational gap. December observers will see the aftermath without knowing exactly what happened. They'll see whatever state 3I Atlas is in post-perihelion, but won't have the detailed observational, record of the perihelion passage itself, the juice data, when it finally arrives in February, will fill that gap retroactively. But for the intervening months, interpretation will rely on inference rather than direct observation. Suppose December observations show 3I Atlas, intact and on a trajectory consistent with natural outgassing. That would support the conventional comet hypothesis. The unusual perihelion chemistry and other anomalies would remain, interesting but explicable within natural frameworks. The story would likely fade from public attention as the object becomes just another interstellar visitor. Unusual but not revolutionary. Alternatively, suppose December observations reveal something unexpected. Multiple objects where one used to be, but with separation characteristics inconsistent with natural fragmentation, or trajectory deviations that exceed plausible outgassing effects, or spectroscopic signatures that don't match any known cometary composition. Any of these would reignite the debate and demand explanation. The challenge with any anomalous observation is distinguishing genuine anomalies from artifacts. Instrumental errors happen. Atmospheric effects can distort measurements. Data processing mistakes occur before declaring something truly anomalous. You need to rule out mundane explanations. This requires cross-checking observations from multiple independent sources, using different instruments and different observers. If everyone sees the same thing despite using different equipment and methods, confidence in the reality of the observation increases. Amateur and professional observers during December will effectively conduct this cross-validation. If one telescope shows something strange but others don't, you suspect an instrumental issue with that telescope. If multiple telescopes at different locations all show the same feature, you gain confidence it's real. The distributed network of observers provides redundancy and error checking that single-facility observations lack. Social media will amplify whatever gets observed. Every image, every measurement, every interpretation will get shared and discussed. This creates benefits and drawbacks. The benefit is rapid information dissemination. Interesting findings spread quickly, attracting attention and additional observations. The drawback is that premature or erroneous reports also spread quickly, potentially creating confusion before corrections can catch up. Scientists prefer to verify results before announcing them publicly. The traditional process involves collecting data, analyzing it carefully, writing up results, submitting to peer review, and only then publishing. This deliberate pace ensures quality but sacrifices speed. Social media inverts that priority, favoring speed over thoroughness. Observations get posted within hours of collection, often with minimal analysis, sometimes with speculation exceeding what the data supports. This tension between scientific caution and public impatience plays out with every high-profile astronomical event. 3I Atlas will be no exception. The first images showing it post-perihelion will circulate immediately. People will zoom in, enhance contrast, look for features. They'll compare to pre-perihelion images, searching for changes. They'll make claims about what they see, some accurate, some not. Professional astronomers will work through their standard procedures, regardless of social media noise, and they'll collect observations, reduce the data, apply calibrations, fit models, and eventually publish results through journals and databases. This scientific record will provide the authoritative account of A3 Atlas's behavior, but it will emerge weeks or months after the initial social media flurry. What matters ultimately is whether A3 Atlas's December appearance forces any revision to our understanding. If it behaves like a comet, following predictable physics, displaying natural outgassing signatures, maintaining trajectories consistent with gravitational and rocket forces, then it confirms we understand these objects reasonably well. Unusual chemistry and unlikely trajectories make it interesting, but not paradigm-breaking. If it does something we can't explain naturally, something that demands invoking processes or technologies beyond current comet models, then December 2025 becomes a historically significant month. The first confirmed observation of something demonstrably artificial in our solar system would reshape astronomy, astrobiology, and human civilization's understanding of its place in the universe. The stakes, in other words, are high, not in any immediate practical sense. A3 Atlas poses no danger regardless of its nature, but in terms of knowledge, of what we learn about the universe and what exists beyond Earth, the December observations could matter enormously, or they could simply add another data point to our catalog of interstellar objects. Interesting but not revolutionary. We won't know until the observations happen. Until then, speculation continues, shaped by incomplete data, competing interpretations, and the hopes or fears people project. To this mysterious visitor from the depths of space. Chapter 10. The Pattern and the Silence. Let's step back from the technical details, the spectroscopy and all, battle mechanics and observation campaigns, and consider the broader pattern that 3 Atlas exemplifies. This isn't the first time an astronomical discovery has triggered speculation about non-natural origins. It won't be the last. Understanding why requires examining how we process unusual observations and what happens when institutions control access to information that the public desperately wants. Oumuamua established the template when astronomers detected the first confirmed interstellar object in October 2017. Its unusual properties immediately sparked debate. The elongated shape, the non-gravitational acceleration as it left the solar system, the lack of visible outgassing despite that acceleration, all of it seemed strange. Avi Loeb proposed it might be a light sail, a thin reflective structure pushed by solar radiation pressure. Most astronomers favored natural explanations, probably a comet with unusual outgassing characteristics or a debris fragment from a disrupted body. The controversy played out in scientific journals, in popular media, and across social media. Some scientists expressed frustration with the extraterrestrial hypothesis, arguing it was premature and unsupported. Others defended the value of considering all possibilities, even unlikely ones, when dealing with unprecedented observations. The debate revealed philosophical differences about how science should handle ambiguous evidence for extraordinary claims. 2I Borisov, discovered in August 2019, provided a contrast. It looked and behaved like a comet from the moment of detection. Clear coma, obvious tail, spectroscopic signatures matching known cometary composition. Trajectory changes consistent with outgassing. Nobody proposed alien origins for Borisov because nothing about it demanded exotic explanation. It represented what astronomers expected interstellar comets to look like, based on our understanding of how solar systems form and eject material. 3I Atlas lands somewhere between these extremes. It shows cometary activity unlike Oumuamua, but it also displays unusual properties, the chemistry, the trajectory statistics, the size ambiguities that distinguish it from typical comets like Borisov. Whether those unusual properties require exotic explanations or just reflect natural variation within the broader population of interstellar objects remains the core question. But beyond the specific scientific debates, 3I Atlas illustrates something about information control and public trust. When NASA's Mars orbiters were positioned to capture detailed images, when the timing was perfect for answering key questions about the object nature, the government shut down. Maybe that timing was genuinely coincidental. Maybe bureaucratic dysfunction rather than deliberate concealment explains the missing images. But the optics are terrible. People naturally assume agencies that routinely manage complex space missions can handle image release during shutdowns if they want to. The perception, whether accurate or not, is that someone made a choice about what to release and what to withhold. That perception fuels conspiracy theories and erodes trust in institutional science communication. This connects to a longer history of government secrecy around space-related observations. The United States military operates satellites that image Earth's surface with extraordinary resolution. Those capabilities remain classified. The specific details of what they can see, how they process images, what they're looking for, all of it stays behind security walls. The justification is national security, the need to protect intelligence-gathering methods, and prevent adversaries from knowing what we can observe. But that secrecy creates suspicion about what else gets hidden. If they classify some space observations for national security, might they classify others for different reasons? If the government discovered evidence of extraterrestrial technology, would they announce it publicly or keep it secret? The classification infrastructure exists. The precedent for withholding space-related information exists. Connecting those dots, fairly or not, leads to assumptions about cover-ups. Similar patterns appear in other domains. When the Pentagon released UAP videos in 2020, confirming that military pilots had encountered aerial phenomena that defied easy explanation, it validated claims that UFO researchers had been making for decades. The government really was tracking unexplained aerial objects. They really did have footage they hadn't released. The conspiracy theorists who said we're not being told everything were correct. In that specific case, this doesn't mean every conspiracy theory is true, most aren't, but it means institutional credibility suffers when agencies that previously dismissed topics as nonsense later admit they were taking those topics seriously all along. The whiplash undermines trust. If they were wrong or misleading before, why should we believe them now? 3i Atlas sits within this complex landscape of trust, transparency, and speculation. Maybe it's just a comet. Maybe the anomalies are artifacts of incomplete observations and will disappear as more data accumulates. Maybe the missing NASA images will eventually be released, showing completely ordinary surface features, or maybe something stranger is happening, either with the object itself or with how information about it is being managed. Without access to the full data, the public can't evaluate these questions independently. We're dependent on institutional gatekeepers to release information, to provide context, to explain what they're seeing. When those institutions go silent at critical moments, people fill the vacuum with speculation. Some of that speculation is reasonable, asking legitimate questions about observation timing and data availability. Some is wild, connecting 3i Atlas to unrelated conspiracy theories about secret space programs and alien contact. The challenge for scientists working within institutions is that transparency has limits. Some data requires careful calibration before release, because raw observations can be misleading. Some information is restricted by international agreements about satellite capabilities. Some results need peer review before public announcement to avoid spreading premature conclusions. All of these are legitimate reasons for not immediately releasing everything. But from an outside perspective, those justifications look like excuses when excitement builds around a discovery, when public interest peaks, when everyone wants to know what's happening. Being told you have to wait months for data to be processed feels like stonewalling. The fact that there are good technical reasons for delays doesn't change the emotional response. This tension won't be resolved by 3i Atlas alone. It's structural, built into how modern science operates within institutional frameworks that have their own priorities, constraints, and risk tolerances. The scientific community values careful verification. The public values immediate transparency. Social media rewards speed over accuracy. Government agencies prioritize control over disclosure. These competing values clash repeatedly whenever controversial topics arise. What 3i Atlas represents, beyond its specific properties as an interstellar object, is a test case for how we handle unusual observations. In an era of distributed information and institutional distrust, the traditional model, where experts make pronouncements and the public accepts them, is broken down. People want evidence, not just conclusions. They want to see the data, run their own analysis. Amateur astronomers, downloading NASA's raw image archives and processing them independently, exemplify this shift. They're not content to wait for official releases. They're not willing to simply trust that experts will tell them everything important. They take available data and extract information themselves. Sometimes their work catches things official channels miss. Sometimes they make mistakes that better calibration would avoid. But the impulse to verify rather than trust reflects broader cultural changes about authority and expertise. Science adapted to previous cultural shifts. When the printing press enabled wider distribution of knowledge, when public education expanded literacy, when universities opened enrollment beyond wealthy elites, the scientific community adapted its communication methods. The current transition to social media and distributed information networks requires similar adaptation. Scientists need to figure out how to maintain rigor and accuracy while operating in environments that reward speed and engagement. 3. Atlas will eventually leave the solar system. By late 2026 or early 2027, it will have crossed Neptune's orbit and headed back into interstellar space. The observations will end. The object will fade into the distance, too far and too faint for our telescopes to track. Whatever we learn about it, we'll learn before it disappears. After that, it becomes another entry in databases, another reference point for future researchers studying interstellar object population. But the questions 3I Atlas raises will persist. Questions about how we evaluate unusual observations. Questions about what evidence justifies exotic hypotheses. Questions about institutional transparency and public access to data. Questions about how science operates in the modern information landscape. These aren't purely academic concerns. They affect how society makes decisions about everything, from space exploration priorities to research funding to science, education. If 3I Atlas turns out to be just a comet, it will have served a valuable purpose anyway. It forced these conversations. It revealed the gaps in our observational capabilities, the limitations of our data release systems, the challenges of communicating uncertainty to public audiences. Those lessons apply beyond this one object. And if 3I Atlas turns out to be something more than a comet, if December observations or JUICE data reveal properties that can't be explained naturally, then the conversations become even more important. How humanity responds to confirmed evidence of extraterrestrial technology will depend partly on the trust relationships between institutions and the public. If people believe agencies are being transparent, response can be coordinated and thoughtful.